Welcome back to this specialization on high performance and embedded computer architecture. This lesson starts a new course on multi-core processors, processors that contain multiple processing elements or cores. Around the year 2005, industry moved to multi-core designs to increase the performance of their processors, and the purpose of this lesson is to explain why. As usual, I inform you of the text this lesson is based on. It is based on section 5.1 of the textbook by Hennessy and Patterson. Several slides, however, cannot be found directly in the textbook, but have been obtained from other sources. Here are the overall objectives for this course. First, after this course, you should be able to explain the reasons why industry has moved to multi-core design. They never wanted to go to multi-cores, but technology constraints forced them to go to multi-core systems. Second, you should be able to mention some challenges of parallel processing and, given some parameter values, calculate the impact of these challenges. Third, and this may be the main focus of this course, you should be able to explain the cache coherence problem and why it is needed in shared memory multiprocessors. Thereafter, I will explain the snooping MSI coherence protocol, MSI. MSI stands for Modified Shared Invalid and represent the states each cache block can be in this cache coherence protocol. Fifth, you should be able to explain why distributed shared memory is more scalable than bus-based shared memory systems and how cache coherence can be maintained in such systems. Furthermore, in any shared memory system, we need to synchronize when shared data is written by one thread and read by another, and I will describe some special instructions that should be used to synchronize. Finally, I will provide a brief introduction to a very difficult topic named memory consistency. Roughly speaking, the memory consistency model defines the order in which shared memory accesses take place and is needed to reason about the correctness of parallel programs. This figure appeared in an article by Herb Sutter called "The Free Lunch is Over: A Fundamental Turn Toward Concurrency in Software," and is based on several sources. It shows the trend of Intel CPUs. The horizontal x-axis shows the years from 1970 up to 2010, and the vertical y-axis shows several trends indicated by colored lines. The green line at the top shows the number of transistors on a chip in thousands and corresponds to Moore's law. The number of transistors roughly doubles every 18 months. Notice that the vertical axis has a logarithmic scale, so a straight line corresponds to an exponential increase. The green line shows that Moore's law still holds, so we can still put more transistors on a single chip, on a single integrated circuit. While it is expected that Moore's law will come to an end in the not so distant future, until now it has remained valid. The dark blue line shows the frequency or clock speed in megahertz. It shows that until approximately 2003, clock speed has also increased exponentially. In other words, computer architects and microelectronics engineers have been able to keep up with Moore's law, to translate more and smaller transistors to higher performance. Around the year 2003, however, something happened. Clock speed no longer increased but stayed constant at approximately 3 GHz. The blue line shows the power consumption in watt. It also increased exponentially up to the year 2003, but thereafter it stayed roughly constant at about 100 watt. So it is naturally to suspect, is this the problem? Are we unable to provide more power to the chip? Well, not really. There are many devices that consume more than 100 watt. So if we are willing to pay for the high electricity bills, this should not be the main issue. Finally, the purple line at the bottom shows the performance per clock cycle or instructions per cycle or IPC. It shows that while superscalar designs have been able to exploit some instruction level parallelism, it peaked at about 5 instructions per cycle. It corresponds to what we talked about in a previous lesson, that ILP is limited and that more and more effort is required to extract more ILP. On the previous slide, I talked about power consumption, but at the same time said that it can't be the main limitation. So what is the problem? The main problem is power density, or watts per square centimeter. Power density translates to heat, and there's only so much heat that can be dissipated before the chip starts to break. That's why high-performance CPUs have fans to cool the CPU. To illustrate this problem, this figure here shows the power density of Intel CPUs. Notice again the logarithmic y-axis. The figure has been shown by Fred Pollack from Intel already in 1999, which is why the Pentium 4 is the last CPU depicted. The figure shows that the power density has also been exponentially increasing. Well, why is this a problem? Can't we cool the CPU sufficiently? Well, this point corresponds to the power density of a hot plate, about 10 watts per square centimeter. This can still be cooled. However, if we would continue on this line, we would soon be at the power density of a nuclear reactor. As my colleague Avi Mendelsohn put it once, since cell phones contain CPUs, we can't have the entire human race walking around with a nuclear reactor in their pockets. Furthermore, if we would further continue on this line, we would soon reach the power density of a rocket nozzle, and a few generations later, the power density of the sun's surface. Needless to say, we are unable to cool down the sun's surface. In summary, we are confronted now with several walls. First, there is the power wall, or more precisely, the power density wall. Since power increases with clock frequency, we cannot increase the clock frequency anymore. As David Patterson put it once, no one knows how to design a 15 GHz processor. Second, there is an ILP wall. For various reasons, we cannot extract more instruction level parallelism from programs. Third, there is a memory wall. Memory is extremely slow compared to the CPU, and somehow we need to hide the memory latency. But Moore's law still continues. We can still cram more transistors on integrated circuits. So the question is, confronted with these walls, how can we increase performance when we have more transistors but cannot make them faster anymore? The solution that the general purpose computing domain has chosen is multi-core processors. So instead of developing a faster processing core, we provide multiple of them. This figure here shows a multi-core processor with 4 cores. I must admit, I can't remember anymore which multi-core processor it is. There are some other factors that have led to the multi-core revolution. First, there has been a growing interest in high-end servers. High-end servers have become more important because they play a critical role in cloud computing. Second, the number of data-intensive applications has grown significantly, driven by the availability of massive amounts of data on the internet. Third, industry has realized that desktop performance is less important, except for graphics, at least. CPUs are fast enough to execute typical desktop applications. Furthermore, highly compute and data intensive applications are now being done in the cloud. Fourth, the understanding of how to use multiprocessors effectively has increased, especially in server environments where there is significant, natural, I would almost say, easy to exploit parallelism. Fifth and finally, multi-core designs also reduce the non-recurrent engineering costs because the design can be simply replicated rather than having to develop a completely new design every generation. As a result, all major microprocessor vendors have switched to multi-core designs. This table summarizes some multi-core designs from different vendors, but in the interest of time, I will not discuss it in detail. This completes this lesson. Thanks for watching. In the next lesson, I will give some classifications of different multi-core designs. Hope to see you back.